Angular momentum and rotational kinetic energy are going to be the topics of this lesson in my brand new general physics playlist, which when completed will cover a full year of university algebra-based physics. Now, we've seen a lot of different rotational or angular analogs for a lot of different translational terms we visited, and we're going to hold true to that in this lesson as well. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. All right, we're going to start off with just a little bit of review. So summarizing every corresponding rotational or angular analog we've had for a lot of the translational terms. We're going to summarize them all here and add a couple of new ones as well. And so the table that's here on the study guide, I'll just make sure it shows up on your screen here. So, but for displacement, we have a rotational, or in this case, angular displacement analog. We have angular velocity, so we have angular acceleration. Instead of mass, we have the moment of inertia. Instead of force, we now have torque. There's a Newton's second law analog in a rotational sense as well, we've seen. And now we've got a couple of new ones. And the first one here is going to be momentum. Now, translational momentum, we had P equals mass times velocity. So in a rotational sense, so we use L for angular momentum. So instead of mass, again, in a rotational sense, we have moment of inertia. And instead of velocity, we have angular velocity. And so now we've got a term for our angular momentum. And just like we had conservation of momentum, we were dealing with like collisions and stuff, we're going to see conservation of momentum in this section as well. Now, in similar fashion, we had kinetic energy and translational kinetic energy. We had 1/2 mv squared. So, well, now we have to be specific. We're going to call that translational kinetic energy with a little t there. So, and then because we're going to have a rotational analog, we'll symbolize with a little r, or some books will use ROT, same diff. So, and in this case, again, instead of mass, we use moment of inertia, and instead of velocity, we now have angular velocity. And so there is now our term for rotational kinetic energy. And just like back a few chapters, we talked about conservation of mechanical energy and things of this sort. Now we've got a new kinetic energy term to incorporate into there. So let's dive into a couple of new things. And again, we'll talk about conservation of momentum and conservation of mechanical energy, now taking into rotational stuff into account with the mechanical energy. So conservation of momentum, we'd simply say, L initial equals L final, or I initial omega initial equals I final omega final. So now if the object that we're talking about hasn't changed in any way, shape, or form, then the moment of inertia shouldn't have changed either. So, but in some cases, in case something, breaks apart or something like this, we put the initial and final under the moment of inertia there as well, just in case that we can count for all possible situations. But there's your conservation of momentum. So, and now, we've had kinetic energy plus potential energy equals, we'll save a little room, kinetic energy plus potential energy. So as our conservation of mechanical energy, and the big thing we're going to do here, so is add an additional kinetic energy term. That way we can take translational and rotational. So in all of these, the initial terms, and again, add another kinetic energy term. And so translational and rotational, and for all these terms, final, and there's our conservation of mechanical energy. So if we have no work being done by non-conservative forces, mechanical energy is conserved, just like we saw back in chapter 5. All right, a couple of other new things here. So rotational work. Well, we saw work in a translational sense was force times displacement. And that displacement can show up in a couple different ways, like delta x if we're talking about one-dimensional problems, but delta r is pretty common. Well, in our new sense now, again, in a rotational sense, we don't talk about force, we talk about torque, and your displacement is now your angular displacement, delta theta. And so now we've got a term for work here performed by a torque, in this case, rather than a force. Cool, and these are the new things, but again, they've all got translational analogs, so they're not going to be completely unfamiliar to you. So, and now let's see how they're used. So the first problem here says, an ice skater with a moment of inertia of 2.0 kilogram meter squared is rotating with an angular velocity of 5.0 radians per second. What is their angular momentum and rotational kinetic energy? There's a second half to this question, but we're going to stop right there first. So we want their angular momentum. So L equals I omega, and we want their rotational kinetic energy. 1/2 I omega squared. And from here, it's plug and chug. We're given both the moment of inertia and that angular velocity, which we can plug and chug into both of these. So in this case, moment of inertia, again, 2.0 kilogram meter squared. So angular velocity, 5.0 radians per second. So, and in this case, if you recall, the radians is kind of like the unitless unit, and so your units are going to be kilogram meter squared per second for angular momentum here, and 2 times 5 is obviously 10. So kilogram meter squared per second. In this case, we want 2 sig figs, so maybe we make this 1.0 times 10 to the first kilogram meter squared per second. My preferred way to get that second sig fig when it's a 0. But take your pick. And then for rotational kinetic energy here, 1/2. And again, the moment of inertia supplied is 2.0 kilogram meter squared. Angular velocity, 5.0 radians per second. Don't forget to square it. And plug and chug from here. So 5 squared is 25. So, but 2 times 1/2 is just 1. So it just ends up being 25 here. And as always, it's going to have units of joules for energy. In this case, 1 and 2 sig figs. We've got 2 sig figs. Life is good. Okay, so that's the first half of the problem. Second half of the problem says, by tucking in their arms, the ice skater's moment of inertia decreases to 0.50 kilogram meter squared. What is their resulting angular velocity? So we hinted at this in the last lesson. So when an ice skater tucks in their arms and legs, they're pulling more of their mass closer to the axis of rotation. That lowers their moment of inertia, which increases their angular velocity because of the conservation of momentum here. And so in this case, with that conservation of momentum, again, omega I equals I final, omega final. And in this case, they changed their moment of inertia, and we can account for that here. So initial moment of inertia was 2.0 kilogram meter squared. Initial angular velocity, 5.0 radians per second. Final moment of inertia, 0.50 kilogram meter squared. And the question is, what is that final angular velocity here? And again, we could reason this out as well. So in this case, what happened to their moment of inertia? Well, it went from 2 to 0.5. It went down by a factor of 4. And there's an inverse relationship here between moment of inertia and angular velocity. And so if the moment of inertia went down by a factor of 4, the angular velocity is going to have to go up by a factor of 4. And so in this case, solve for that final angular velocity. So 2 times 5 is 10. 10 divided by 0.5 is divided by a half. Same thing as multiplying by 2. And we're going to get 20. And in this case, radians per second. And again, we can put the bar over to get 2 sig figs, or we can make this 2.0 times 10 to the first radians per second. Take your pick. So the next two questions look similar, but they do look like independent questions. But the first one we're going to do here technically doesn't even really belong to this chapter, but it's there for comparison's sake, as we'll see. And so the first one here says, a 10.0 kilogram block slides down a 5 meter tall frictionless incline. What is its velocity at the bottom of the incline? So there's a couple different approaches we could take to solving this, but one of the ones we learned, probably the easiest route here, is conservation of mechanical energy. So and in this case, right now, it's got its maximum amount of potential energy. So by the time it reaches the bottom of the incline, it will have the lowest amount of possible potential energy. We'll call it 0. So at the top, it's released from rest, so it has 0 kinetic energy. But at the end, so it's going to have its maximum of kinetic energy. And so with that conservation of mechanical energy, the big thing is that there's nothing new here. There's no rotational term. This thing is not rotating or spinning in any way, shape, or form as it goes down. But the next example will be a little bit different. So but we can see here that we'll ignore the rotational term here, but we're just going to have kinetic energy translational, which initially is 0. And so it's just that potential energy, which is mgy initial. So where the height is 5 meters. And then that's going to equal, and again, at the end, when it's at the bottom of the incline, there's no more potential energy at that point. It's all just translational kinetic energy. And so 1/2 mv final squared. So, and if you notice, the mass falls right out. We didn't actually have to know that it weighed 10 kilograms. Gravity doesn't care about your mass. It's going to affect every mass the same. And in this case, rearrange this. The final velocity, a result we saw a few times back, a couple chapters, was the square root of 2g times that initial height. And from here it's plug and chug, and so in this case, final velocity, square root of 2 times 9.8 meters per second squared times that height of 5.0 meters. So, and from here we can do some plug and chug, but you can kind of see that, well, 2 times 10, if we round it up, would be 20, and times 5 would be 100, and square root of 100 is 10. Well, it's going to come out just a little bit lower than that in this case. And so in this case, 2 times 9.8 times 5 is 98 instead of 100, and we'll take the square root and get an answer just under 10, 9.9. Let's see, we want 2 sig figs? Yeah, so 9.9 meters per second. Okay, so things are going to be a little bit different on this next one, and we should be able to qualitatively predict something. So let's read the question real quick. So a 10.0 kilogram solid sphere, the moment of inertia of 2/5 mr squared is provided, but with a radius of 0.25 meters, rolls down a 5 meter tall incline again. What is the translational velocity at the bottom of the incline? And the question we should be able to answer is, should it be slower or faster than 9.9 meters per second when it reaches the bottom? So, and the reasoning should go like this, is right now it only has potential energy, but when it reaches the bottom and it's going to be rolling, so when it reaches the bottom, it's not going to have just translational kinetic energy, it's also going to have rotational kinetic energy. And so because some of that initial total mechanical energy is now dispersed between two types of kinetic energy, there's not going to be as much available for purely translational kinetic energy, and so its translational velocity is not going to be able to be as high. So it still has a mass of 10 kilograms, just like this one here. It still starts out with the same amount of potential energy as the sphere as it did with the block, but because that potential energy is now turned into two different types of kinetic energy at the bottom of the incline, the translational kinetic energy is not going to be as high, and that translational velocity, again, not as high. All right, so let's see how this works. So again, initially it doesn't have either type of kinetic energy, only potential energy. So, and again, that's going to be mgy initial. So, and that's going to equal your translational kinetic energy at the bottom, so 1/2 mv final squared, but also now your rotational 1/2, let's get that right, 1/2 I omega final squared. Cool, so what do we do from here? Well, keep in mind, you recall that V was equal to R omega, which means that omega is equal to V over R. And we can substitute that in right there so that we can have this entire expression written in terms of the translational velocity which we want to solve for. So in this case, we'll get, oh, and one thing to note, actually, we'll get that later. So mg yi equals 1/2 mv final squared plus 1/2. And again, that moment of inertia was provided in the problem. It's 2/5 mr squared. So, and then times, in this case now, omega squared is v squared over r squared. Once you square it. Now let's have a little fun. Now, one thing to note, I already made this a lowercase m. It was written as a capital M. It's the same m. Same thing with the r, though, as well. The radius here is the same radius that's present in the problem here as well. So we should write it the same. And we can see here that that's actually going to cancel. So now we're going to have mg yi equals 1/2 mv final squared plus, we can cancel out those 2's, we're going to get 1/5 mv squared. 1/2 plus 1/5, common denominator is 10, so 5/10 plus 2/10 is 7/10. So, and notice again that mass falls out of this equation. So when we go to solve for our final velocity here, it's now going to equal 10 over 7 times g times the initial height. Take the square root. And notice a little bit different than what we saw here. Instead of 2 times g times the initial height, it's now 10/7, which is less than 2 times g. And so because that's less than 2, the overall final translation velocity should come out lower as well. Let's plug those numbers in. And so in this case, square root again, 10/7 times 9.8 meters per second squared times that initial height of 5.0 meters take the square root, and that should get us our final translational velocity here. All right, so 10 divided by 7 times 9.8 times 5.0 gets us 70, and if we take the square root of that, it's definitely going to come out lower than the last answer. 8.4, rounded to 2 sig figs, meters per second. And we do see that that is definitely lower than the 9.9 meters per second we had for the block over here. Now, one last thing to note about this is on the first one I talked about this block sliding down a frictionless incline, but I didn't say the same thing for the sphere here. I didn't say it was frictionless. Well, here's the deal. If it were frictionless, then the problem would be no different. This thing would just slide down without rotating. It's only because there is friction between it and the incline that actually it has any propensity to roll whatsoever. So we had to be careful not to phrase this as frictionless, or else there would have been no rotation. We would have got the same answer as we did for the block. So the next question is going to involve a disc brake, similar to the one we saw in the last lesson. The question reads, a brake causes a frictional force of 1,000.0 newtons on the outer rim of a wheel in the direction opposite the tangential velocity if the moment of inertia of the wheel is 50.0 kilogram meter squared and its diameter is 20.0 centimeters. How much work is performed by the brake to bring the wheel to a complete stop from an initial angular velocity of 40.0 radians per second? So let's write some more information here. So our final and initial angular velocities, the initial was 40.0 radians per second, and we want to bring it to a complete stop, so the final angular velocity here is going to be 0. Now we've got a little work cut out for us, so because here effectively we're on to find the work with a new definition here, so torque times your angular displacement. Well, the torque is not so bad. If we take a look right where the brake comes in contact with the wheel, let's say that the wheel is moving in the counterclockwise direction, the tangential velocity right at that point so would be pointing to the left, right where the brake comes into contact. So friction is a non-conservative force, always opposes the motion, so it would point exactly in the opposite direction. And if we look at the relationship here, it is perfectly perpendicular to our lever arm. And so calculating the torque, not so bad. In fact, we can do it in our head real quick. So frictional force was 1,000 newtons. So, and we can see that the radius here, the lever arm, is 10 centimeters or 0.01 meters. Well, 1,000 newtons times 0.01 meters is going to be 10 newton meters for our torque. So getting the torque, not so bad. Getting the angular displacement, pain in the butt. So to get that angular displacement, based on what we know, not the easiest thing in the world. So you got a couple different approaches you could take, but at the end of the day, it's going to involve a lot of rotational kinematics. So if you do sum of the torques equals I alpha, well, we know the torque here again is going to be 10 newton meters. So the moment of inertia is provided, and we could use this to find that angular acceleration. And the reason we do this is because the angular acceleration is equal to the change in the angular velocity over the change in time. Because we know the initial and final angular velocities, we know the change. And we know the angular acceleration from the Gov equation, so we could solve for the time would be one route to go. And once you solve for the time, you could go a couple different routes in using rotational kinematics to then solve for the angular displacement. Or you could just say, screw the time and, do your final angular velocity squared equals initial angular velocity squared plus 2 times your angular acceleration times your angular displacement, and use that kinematics equation instead. We know the initial angular velocity, 40 radians per second. We know the final is 0. We got the angular acceleration from the sum of the torques equation. We could get it that way, but it's still a pain in the butt, and there's an easier way. So you guys learned the work-energy theorem, or work-kinetic energy theorem, and you learned that the net work on an object is equal to its change in kinetic energy. So in this case, there is a rotational equivalent, and it's the net work performed by torque is equal to the change in rotational kinetic energy in this case. So, and that's ultimately what we're being asked is what is the work performed by the friction? In this case, it's the work done by a torque due to the friction of the brake. And we can just figure out the change in rotational kinetic energy, which is really straightforward because we have the initial and final angular velocity, we have the moment of inertia, and it's much simpler plug and chug here. So work done by our torque is equal to the change in rotational kinetic energy. That's 1/2 I omega final squared minus 1/2 I omega final, how about initial, squared. So work done by a torque, 1/2. So that moment of inertia was provided, 50.0 kilogram meters squared. Your final was 0. I guess I should have just zeroed that out to begin with. But then minus 1/2, 50 times, or 50 kilogram meters squared times 40.0 radians per second. Don't forget to square it. And we're ready to let our calculator do some work for us. Yeah, let's let the calculator handle this. So yeah, that first term again goes to 0. But that second term, so we can see the work is going to come out negative here. Well, let's not write that in red. It's going to be negative here, and that makes sense. So the kinetic energy is going down to 0, so the work should be negative. It's a reduction in kinetic energy. And in this case, 0.5 times 50 times 40 squared is 40,000. That's in joules, as work should be. So, and to get 2 sig figs here, again, my preference is simply to write this in scientific notation. So negative 4.0 times 10 to the 4th joules. And I guess you could technically write that in kilojoules, or look for that in kilojoules if it were a multiple choice question. Now, if you were to go about doing this the other way, again, we already figured out that the torque would be 10 Newton meters. Well, it turns out that if you did solve for this, that angular displacement would be 4,000 radians, and 10 Newton meters times 4,000 radians. So, and technically, the torque would end up being negative because the force is opposite the motion. So technically, negative 10 Newton meters times 4,000 radians would still get you negative 40,000 joules if you solved it that way. If you found this lesson helpful, consider giving it a like. Happy studying.